Okay, hello everybody. We don't have any guests today, so I'll just continue on my own. So basically what I'm going to be doing today is I talked last time about solids. Today I'm going to talk about liquids and their interactions, and then go back to the rest of the other chapter. But now I'm going to use an introduction to kind of move forward. So what I want to do now is go to the PowerPoint and start the presentation. And share the screen with you folks here. Okay, basically what we're going to talk about today is essentially the water and properties of liquids in relation to the nature of the chemicals. We talked before about gases, solids last time, and today we're going to talk about water and the property of liquids. This is an introductory lecture that you may not have in your other classes, in your other lectures with Dr. Powell or Dr. Gerhardt. So I hope you find this informative as well. So what I'm going to do now is go through the slides to kind of introduce them to you and talk about the different ones that are important. The first thing to deal with is water is the most common liquid that we are ever acquainted with. And basically the nature of water, essentially we start off first with what is a liquid, and then how these things interact with each other. And basically the properties of liquids are intermediate between the extremes of gases and liquids. For example, the gas is huge space between a liquid, it fills a container, and then a solid has a shape associated with that, and basically it can be measured easily, measured by length. Okay, and conforms to the shape. So the key thing to understand about the nature of liquids is they're intermediate between gases and solids. The properties of liquid, the particles are close together, they're incompressible, and they have a definite volume. So with a gas, you've got a gas essentially has them all surrounded with a lot of empty space. A liquid, they're all together in a globule or in a vessel like a cup. They have a definite volume associated with that, and the standard volume is milliliters, liters, or quarts, or gallons, other kinds of things related to that, and basically takes the shape of its container. Now, what we're talking about now is phase changes, and I addressed that last time with the previous lecture. When you have a gas and it converts to a liquid, this is called condensation. Liquid to a gas is called vaporization or evaporation. Okay, evaporation. Liquid to a solid is freezing, and then solid to a liquid is melting. This is called a phase change. And that's very, very important to understand the nature of how that works. Evaporation or vaporization is the escape of molecules from a liquid state to a gas or vapor state. So essentially you start off with a cup of water like this, and different water molecules will come off the surface, and that would have what is called a vapor pressure, the vapor pressure of water, and you would use that in this week's lab. And say sometimes it was at 18 degrees Celsius, and then you had a certain vapor pressure water, that was mixed with the oxygen in the flask. Basically, you have the liquid state to the gas or vapor state. The liquid to the vapor contrast is called evaporation. When molecules of higher than average kinetic energy escape from the liquid, the remaining liquid is cooler than it was before they escape. It loses energy. So essentially, evaporation requires heat, uses heat. And you can prove that by just putting cold water on a stove, and heat it up, heat with burner. And basically to keep it boiling, you've got to provide energy to do that. And the remaining liquid is cooler than it was before they escaped. So essentially the kinetic energy, the energy leaves the liquid and then goes to the gas. So here you've got liquid water going to gaseous state, going up above, and basically it's like that. It's all in liquid form, and then it pops up above it. So essentially you have the gas molecules escaping from the vessel of water as it goes up. Sublimation occurs when a solid goes directly to a gas bypassing the liquid state. So for example, if you've got a block of what is called dry ice, which is frozen carbon dioxide, okay, that will go from a solid directly to a gas, okay, and that is called sublimation. Okay, iodine the solid to a gas is very easy to do too. You got a purple solid going to purple gas, and this also requires heat. So you've got to have heat to cause this reaction to take place as well. So heat is on the side of that as well. That is also endothermic. So all these situations are endothermic. Vapor pressure. Vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid. Okay, so basically you got liquid going to a vapor is evaporation. Vapor condensing to a liquid, that's called condensation, going the other way. So basically evaporation one way, the other way. And in a closed system, after a liquid evaporates, some of the water vapor molecules strike the surface of the container and return to the liquid by condensation. So basically, if you've got, again, a cup of water like this, you will have some escaping there. And then if this is cool on the outside, then it'll condense and then go back into the water again, condense. And that would be like water on the side of it, condensing back into the water itself. Molecules in an open beaker evaporate from the liquid and disperse into the atmosphere. Evaporation will continue until all the liquid is gone. That's why if you put a cup of water out in your living room or kitchen, eventually you'll need to put more water in it. I find this to be particularly the case with the cat's bowl of water that I give him. I periodically fill it up, but most of the water is lost by evaporation, even though he does drink from it periodically. He just was drinking from it now. So basically evaporation occurs until all the water is gone. What happens if you have 100% of humidity? Okay, if you have 100% humidity, that means the atmosphere is full of water as to what you can have is full. Basically, you will get a situation where you'll get a situation where basically it will go out and in at the same time. Okay, so basically you have 100% humidity, the atmosphere is full. And you'll get these coming out, and they will also go back down inside. And that kind of condition outside would be in a situation where it's foggy. So that's 100% humidity outside. So if you put a cup of water out in 100% humidity, water will evaporate and then condense back into the same bowl, and it won't change anything. Molecules leaving the liquid if they're confined to a limited space, the concentration of vapor increase until the equilibrium has been established, and this is called 100% humidity. In the small space. Now, measurement of vapor pressure at 20 degrees and 30 degrees Celsius. This is where they get the numbers for what you were dealing with this week in lab. The vapor pressure is independent of the amount of liquid and vapor present. It increases with temperature. So you increase the temperature, the pressure will go up. That's why, for example, you got boiling water on the stove with a tea kettle, the water boils and it essentially comes out, causing it to whistle and blowing steam out the vent. That is vaporized water coming out. And basically, with the temperature going up, the vapor pressure increases. So if you were to measure this kind of relationship at 20 degrees, you use what is called a manometer to do that. And this would be the vapor pressure of water in this situation, which would kind of indicate what it is. The system is evacuated with a vacuum. The mercury manometer shows the equal pressure in both legs. You have equal pressure here, right here. Then water is let into the system. Water is let into the system there through the valve. Okay, and then at the temperature of 20 degrees, the water begins to evaporate. Okay, no longer a vacuum. The water exerts a vapor pressure, which is indicated by the manometer. Those are how they essentially, you got experiments that got the table you used. You used for this week's lab, for the lab. So this is important. Okay. When equilibrium is established, the vapor pressure of the liquid inside remains constant at 17.5 torr. Some of you at 18 degrees Celsius, I'm just remembering, some people at 18 degrees C, others at 17 degrees C, others at 21 degrees C. So basically, they will all be put on the chart that you used yesterday to get the numbers for your experiment. If the temperature is changed to 30 degrees, more of the vapor comes off of this, causing more collisions, a greater pressure in that. It shifts going up and it becomes 31.8 torr. The equilibrium is reestablished. The vapor pressure has now increased to 31.8 torr above. Now, here are some examples of water, the vapor pressure in torr at different temperatures. So basically, the numbers you were dealing with were in this area here. So some of you had 17.5, others had this, but the key thing is with this, the vapor pressure there. But if you've already got a gas or something that's very volatile, this vapor pressure could be really high. But if you notice here, this is the boiling point. That's at 760 torr. So at 1 atmosphere pressure, at 1 atmosphere pressure, okay, 100 degrees Celsius is where you have the vapor pressure of the water equals 1 atmosphere. And that's where it goes all to a gas. It boils. So essentially you've got water boiling. That's where the vapor pressure is equal to 1 atmosphere. So if you look at the different examples here with the vapor pressure at any time, ethyl ether has a higher one than ethyl alcohol, greater than water. The rate of evaporation of ethyl ether is faster than ethyl alcohol and water. That's why with ethyl alcohol, you put it on your skin, it evaporates, your skin gets cooler. So this is the active ingredient in rubbing alcohol. So essentially, this is some kinds of rubbing alcohol have that in it to cool down your skin or make it feel better. The rate of evaporation is proportional to its vapor pressure. Now, the next concept is what is called volatility. And then substances that evaporate readily are said to be volatile. Okay. The temperature is, say, 20 degrees C. The vapor pressure of ethyl ether is 42.2 torr, which is less than atmospheric pressure. So essentially, this is a liquid, but it's volatile. It evaporates really easily. Okay. The vapor pressure of water is 17.5 torr, so it's moderately volatile. And then with mercury, it's very, very small, and essentially it would be non-volatile. Now, the key thing about surface tension is it's all about intermolecular forces. For example, if you've got water, looks like this. Okay, and you put another water molecule next to it that looks like this. This will attract here. And so basically that will give high surface tension. Okay, because of these hydrogen bonds that provide a sort of tension associated with that. Surface tension is the resistance of liquid to an increase in its surface area. It's the result of the liquids at the surface being pulled inward by molecules that lie below the surface due to intermolecular forces. And we talked about that in the previous lecture. And this pulls the surface of liquid into a sphere if there isn't much in there. Substances with large attractions between molecules have high surface tension. So water would be one example. Mercury would be another one. Capillary action is another concept. And basically, you have a tube that's like this, and will suck water up the tube, going up the tube that by capillary action because of the intermolecular forces between the liquid and the tube, like glass. So essentially, you've got forces pulling it up there. The intermolecular forces are relatively strong. So if you got a really thin tube, it will go up as well. So that's the spontaneous rising of a liquid inside. It results in the cohesive forces within the liquid and the adhesive forces between the liquids and the walls. If the adhesive forces between the liquid and the walls of its container exceed the cohesive forces, the liquid will climb the walls of the container. And that's essentially how it works with trees and sap. They have tubes in there, and evaporating from the leaves, and essentially you've got tubes the water goes from the ground to the leaves, ground to leaves. Okay. Now, the meniscus, when a liquid is placed in a glass cylinder, the surface of the liquid shows a curve called a meniscus. And basically, that's when you have a graduated cylinder or something, you have water in it, and it looks like that. So, for example, with a burette, this is the meniscus here at this point. So this is the meniscus associated with that, and that little curve is due to the capillary action next to it, and that is called the meniscus. So basically, you read the level of the burette from the bottom of that meniscus, the bottom of the meniscus. So that could be a graduated cylinder, a concave shape, and you read it from the bottom. So you got adhesive courses between the glass and the water, and adhesive courses between the water molecules too, cohesive forces. So the forces between the glass sides and the water molecules are higher, so you got the concave shape. Now, boiling point. The boiling point of any liquid is the pressure, which temperature the vapor pressure of a liquid is equal to the external pressure of the liquid. So the normal boiling point is as the temperature where the liquid boils at 1 atmosphere pressure. So basically the vapor pressure of water at 100 degrees Celsius is 760 millimeters of mercury, which is 1 atmosphere. Now, one thing I like to ask my students, say for example, Denver is a mile high. So basically Denver, if you have 6,300 feet high, okay? So certain areas of Denver, 6,300 feet, will the temperature of boiling water be higher or lower? Well, it'll be lower there. And so food won't cook as well if you're boiling it. So basically you have to adjust the cooking time to cook it long enough for that to occur. The vapor pressure of water, ethanol, and at various temperatures. Again, this is the example that was dealt with before, and this is water in this state here. So for ethyl alcohol, the vapor pressure in torr, if you notice ethyl alcohol here, this is 812, 7060 is right there. So basically the ethyl alcohol, that's 78 degrees Celsius, that's where it will boil. Here, the temp 760 is in this place, so essentially 760 is in there, so it'll boil a little less than 40 degrees, so around 40. So basically here, you'll have less than 40 degrees for the boiling point of ethyl ether. Water boils when its atmospheric pressure is 1 atmosphere or 760 torr. So here's some example of other liquids or solids, depending on what they are: ethyl chloride, ethyl ether, ethyl alcohol, and then water there. The melting point. And the heat of vaporization. This heat of vaporization essentially is equal to the heat of vaporization is equal to the heat that would be on this. You have heat plus water liquid going to H2O gas, okay? This would be the heat of vaporization to cause that to occur. So basically you have there 2259 joules per gram. And then for freezing, essentially you have here with fusion, this would be going to essentially heat plus H2O solid going to H2O liquid. This is the heat of fusion. This would be the heat of vaporization. Okay, and these are both endothermic processes. The normal boiling points for different substances can be plotted, and you can see how they work regarding vapor pressure, temperature curves for each of them. And it's really quite interesting. They basically determine these curves by doing experiments. The boiling point at any temperature can be found basically just by looking at the different things. So if you've got the in Denver, see Denver, the atmospheric pressure might be like 650 torr. So the boiling point would be like 92 degrees Celsius in Denver. And basically that's a typical curve that you have each of those based on where you are. Freezing point or melting point. This is the liquid changing into a solid, is called to be freezing or solidifying. A solid that is changing into a liquid is said to be melting. The temperature in which the solid phase is in equilibrium with its liquid phase is known as its freezing point or the melting point of the substance. And basically an example would be if you got well mixed ice in water, liquid, and you stir it really well and read it on the thermometer, it should be 0 degrees Celsius on the thermometer. So basically solid to a liquid, if you got ice cubes and a beaker of water, then you have both of them together, you're stirring it really well, and basically you have melting and then refreezing, and basically these changes are called changes of state. So for a pure substance like water, for example, this is a heating curve. You'd have here solid down here. This is the solid to liquid, and notice it's stable. Here is all liquid water, requires heat to get up to that point, liquid to vapor, and notice it's at 100 degrees Celsius. There, 0 degrees Celsius down there, and basically that's the heating heating curve for a pure substance there. Heat of fusion, the energy required to change 1 gram of a solid at its melting point into a liquid is called the heat of fusion. And basically that, if you, a sample problem that would be how many joules of energy are required to change 10 grams of ice at 0 degrees Celsius to water at 20. The heat of fusion of ice is 335 joules per gram. So determine the joules necessary required to melt ice. So that would be the first step of this. You start with the 10 grams. This is the melting portion. The melting portion has to start first. So if I go black to here, this is the melting. So this is where melting is occurring. And notice it's a line that goes like that. You add heat and it just continues to melt. So this is the heat of fusion, And until all the ice is gone, it will stay at the same temperature. Okay, so you start off with that. You get 3.35 times 10 to the third joules. How many joules of energy are needed to change 10 grams of ice to water at 20 degrees? So to heat the water at 10 grams from 0 to 20. The specific heat of water is 4.184 joules per gram degrees Celsius. So you essentially have the combination of them. That's 837 joules. So you add it to the other number you have there. You add those two together, and that gives you your final answer. And notice most of the energy is in melting the ice. The energy required to change 1 gram of a liquid at its boiling point into a vapor is called the heat of vaporization. How many kilojoules of energy are needed to change 20 grams of water at 20 degrees Celsius to steam at that? Again, if you go back to the previous chart, it looks like this, where this is the freezing point, then the water goes up like that, and then it goes like this. This is where it's boiling. So essentially you have here, this is going from 20 degrees Celsius, heat up the water first there to 100 degrees C, and then the boiling occurs there, all the steam. So you got to heat the water first, heat the water. Okay, so you have the mass times the specific heat of water times the change in temperature is the energy. Determine the kilojoules necessary to heat the water. You put those values in there. That's 6.71 kilojoules. Then you do part 2. This is part 1, number 1. And then this is number 2 here. Okay, so the second part, heat of vaporization of water is 2.26 kilojoules per gram. Determine the kilojoules necessary to change 20 grams of water at 100 degrees C to steam. So basically you have those things together. The total heat absorbed by the system is the heat required to raise it from 20 degrees plus the heat required to do both. So you essentially, the total is equal to number 1 plus number 2. And that's related to Hess's law too, that basically you've got both those different things. And next week's lab is essentially going to be about Hess's law, but that's in chemical reactions. But in some respects, these kinds of heating up things, you've got to heat up the water first and then convert it to steam. Now, water carries about 75% of the Earth's surface. We'll never have a shortage of it. 97% of the Earth's water is in the oceans. And believe it or not, when they say there's a shortage of water, if you hear a story saying there's a shortage of water, okay, what that means is a shortage of clean, cheap water. Okay, so in deserts and other places, it's more expensive, but there's not a shortage of water. The key thing is clean and cheap. And that's what concerns people, is how much we pay for it and whether it's clean or not, clean or dirty. About 3% of the Earth's water is in the fresh water, and 2/3 of this is locked up in the polar ice caps, and glaciers. So the key thing to understand is most of the Earth, oceans, has almost all the water. 70 elements have been detected in seawater. There's a whole lot of different examples of that. And basically you got salts dissolved in seawater, in the sea. And those are all that. So essentially you got sodium chloride, sodium bromide, etc. So sodium bromide, etc., etc. Water constituents about 70% of the human body mass. 92% of the blood plasma is water. 80% of muscle tissue is water. 60% of a red blood cell is water. And so water is very, very important for chemistry of the body. Now, various physical properties of water here. Ice and water exist together in equilibrium at 0 degrees C. That's the freezing point. So you got those different relationships there. And at different aspects of that, when it's frozen, the heat of fusion is given there. If you compared it to other ones like H2S and these, basically hydrogen selenide and hydrogen technetide essentially are gases, but water is much higher in the melting point and boiling point because of hydrogen bonding. The density of water reaches a maximum of 4 degrees Celsius. As it cools to 4 degrees Celsius, it contracts in volume and rises in density. When it's cooled from 4 to 0, it expands in volume and decreases density. This is why ice floats. It expands on freezing. And again, it's because of hydrogen bonding. When water changes to ice, the volume expands. The density of the ice is less than that thing. That's why it floats in water. The structure of the water molecule looks like this. You got the electronegativity hydrogen is 2.1, oxygen 3.5, hydrogen has partial positive, oxygen partial negative. The nonlinear structure looks like this. The Lewis dot structure shows the electron distribution around each of them, the bond angle and bond length, and then the orbital structure associated with that. And there is a definite dipole representation of this. So the electronegativity difference there. The hydrogen bonding is all related to this. Basically, you have these things there. Water has the lowest molar mass, but it melts at a higher temperature and boiling point. That's all because of the hydrogen bonding associated with it. And it's an intermolecular bond between both. And the hydrogen bond is formed between the polar molecules that contain hydrogen, covalently bonded to a small, highly electronegative atom. And examples of that would be fluorine, oxygen, and nitrogen. So you can have HF or HO and NH. When hydrogen is attached to one of the small things, it'll be attracted to another one. This dipole-dipole bond will be formed between two molecules, which is called a hydrogen bond. So basically, hydrogen fluoride is also liquid, but it can easily be changed into a gas because of this. Water in the liquid and solid states exists as aggregates in which they're linked together by hydrogen bonds. The formation and chemical properties of water, decomposition is small amounts of, you can decompose it if you want, just by putting electrical current associated with this. The formation of water essentially is hydrogen plus oxygen, giving water here. This is burning of hydrogen. Okay. Neutralization reaction, an acid reacts with the base to form water liquid. And then combustion of hydrogen containing substances leads to water, and methane plus oxygen gives carbon dioxide plus water vapor plus heat, and then metabolic oxygen in living cells, essentially with enzymes, and you get water from that too. Reactions of water with metals and nonmetals, metals that react with cold water to produce hydrogen and a metal hydroxide. Basically, these are typical reactions that will occur. So if you add potassium to water, you'll get hydrogen gas. And you saw that in some of the labs last semester, where you took the calcium metal and you added water to it. And essentially you got calcium hydroxide plus hydrogen gas, okay? And that is one of the experiments you did in last semester's lab. This is what you saw last semester. Metals react at high temperature steam to produce hydrogen and a metal oxide also. So some of those will react with steam to give a similar result. Okay. And nonmetals that react with water, there's a bunch of different examples associated with this. Fluorine plus oxygen will give HF. Chlorine will give a mild reaction, HCl plus hydrochloric acid, and then a mild reaction with bromine. Reactions of water with metals and nonmetal oxides. Basic anhydrides are metal oxides that react. You have calcium oxide plus water goes to calcium hydroxide. Sodium oxide goes to sodium hydroxide. And there's no reaction with some other ones. Acidic anhydrides react with water to form hydroxides. Some examples of that would be carbon dioxide and water. You get carbonic acid. This is an acid, okay, called carbonic. And this is in carbonated water. That's why carbonated water is tangy or soda, okay? SO2 plus water will give H2SO3. Insoluble metal oxides do not react with water there. So there's reactivity. And then hydrates, solids that contain water as part of their crystalline structure are known as hydrates. Water and hydrate is known as water of hydration. And you saw that last semester when you took copper sulfate dot 2H2O or 4H2O, sorry, and you put heat on it, and then you got the copper sulfate plus the water coming off, and you did that in an experiment last semester. Formulated hydrate are written first by the formula, the anhydrous compound, and then adding a dot followed by the number of water molecules present. Looks like that. Water molecules and hydrates are bonded by electrostatic forces between polar molecules and the positive or negative ions of the compounds. These forces are weaker. As a result, the water crystallization can be removed by moderate heating. And you did that in last semester with the copper sulfate. So different examples there, okay? So basically that ends that slide presentation for this part. And now what I want to do is continue with the chapter that I addressed before and basically finish off kind of dovetailing in with the chapter based on where we stopped last time, and then continue for another 15 minutes and then finish off the lecture next week. But this will help you understand this week's lab a little better with what we did with vapor pressure. So hopefully that makes sense, everybody. Okay, so let me go to the next PowerPoint. Okay, now here, I'm going to continue the lecture. Okay, here, for example, as a temperature less than 13 degrees Celsius, tin will transfer there to another form of tin related to the previous thing. That's the nature of solids, some solids. So let's continue here. Now, this is a summary of the phase changes that I was talking about in the previous thing. If you go from a solid to a liquid, this is called melting. Okay, so you got melting there, freezing the other way. Liquid to a gas, vaporization, condensation. This is called deposition this way, sublimation that way. And basically those are the transitions between each of these different materials. The greatest order is the solid form. The liquid is intermediate. This is no flow. The solid will not flow. This will flow, and this will also flow. Okay, so basically this is very speedy at this point in a gas, but basically a liquid will flow. You could pour liquid out of a beaker and see the flow for yourself. The effect of temperature and kinetic energy, you increase the temperature, the kinetic energy of the different molecules will change based on what they happen. The equilibrium vapor pressure is the vapor pressure measured with a dynamic equilibrium that exists between condensation and evaporation. I talked about that in the previous set of slides, where you got equilibrium at that point. The rate of condensation equals the rate of evaporation. And this would be, for example, at 100% humidity. Measurement of vapor pressure. This is an example here of this. Before evaporation and then after. And you can see the vacuum, and the previous slides showed those breakdowns. The molar heat of vaporization is the energy required to vaporize 1 mole of a liquid at its boiling point. And basically, there's a bunch of different examples with diethyl ether, water, and mercury again. And this uses a particular equation here. And basically, in the problems, you may be asked to do these kind of problems in your lecture associated with this. But that's the vapor pressure associated with these alternate forms of them. Can look like this as well, or you can have one like that. The boiling point at the temperature of the liquid is where the vapor pressure of the liquid is equal to the atmospheric pressure. The normal point is where the external pressure is 1 atmosphere. So here's different examples of the different boiling points of different material. And notice water is at 100 degrees C, like we did before. And this is the heat of vaporization, again, that we talked about in the previous set of slides. The critical temperature is the temperature above which the gas cannot be made to liquefy, no matter how great the applied pressure. And basically, that is where you've got the curve like this. This is the freezing, goes up like that to boiling. This is the boil. This is the freezing point. And then you got the gas up. This is the gas, but at a certain temperature, this is the TC up here, where you cannot compress it to cause it to liquefy. And the critical pressure is the minimum pressure that must be applied to provide the liquefaction at that temperature. So carbon dioxide is the critical pressure is 31 degrees Celsius. So basically you can get in a tank liquid CO2 in a tank. So the whole variety of different things that could be put in a tank and made to liquefy. Ammonia is another example. Just making higher pressure will get liquid ammonia in a tank. Here's an interesting experiment where you have SF6, where the temperature is greater than the TC, it's all vapor. Where it's less than TC, it's partly a liquid. And then where it's equal to it, you've got the combination of different factors related to it. And then when the temperature is below the TC, it can also look that way. That's a little experiment. The solid liquid equilibrium, this is the melting point, which the solid and liquid phases that coexist in equilibrium, like that. And basically this is called the molar heat of fusion. And again, water, the molar heat of fusion is 6.01 there, measured at room temperature, where you have 1 mole of a substance at its freezing point. And this is an example of the heating curve. And the TC is up here, the critical temperature is up here somewhere. So here you got a solid, here you got this is the melting, this is where the melting's occurring, this is where boiling's occurring, like that, and then the vapor over there. Solid gas equilibrium, the molar heat of sublimation is the energy required to sublime 1 mole of a solid. And this is related to Hess's law, where you add the 2 parts together. The heat of sublimation is equal to the heat of fusion plus the heat of vaporization. So basically you can get sublimation. This is the heat of fusion, the melting, and this is the heat of vaporization. Together, you get the sublimation going them to both directions. So essentially you've got the combination of this is an example of Hess's law, of which you're going to talk about. You're going to do an experiment with this next week. The phase diagram looks at the conditions in which a substance exists as a liquid, solid, or gas. And for example, with water, the thing that's interesting about water, if at 1 atmosphere you got a solid and liquid, but if you increase the pressure, higher at 0 degrees C, this will liquefy the water. Okay, increasing that. And that's where you have ice skating. Ice skates, they skate on water itself, on water, liquid. That's why they can go so fast on it. Or if you're going outside and you're walking around when it's around the freezing temperature, you can slip on ice fairly easily because you'll liquefy the surface just from the pressure of your feet. And that's a good example of the phase diagrams aspect. Phase diagram of carbon dioxide, however, if you increase the temperature here to vapor to a solid, this is the vapor going to a solid here. With dry ice, if you increase the pressure, it will remain a solid. Whereas here, if you have a liquid at this point and drop the temperature, it'll go to a solid. Or you could even have a liquid at this point and you drop it down, it'll go to a vapor. The increase in pressure on the boiling point of there, essentially you add pressure to it, you'll get a decreased boiling point and an increased boiling point. And then ice skating is particularly interesting there. With ice skates, as I was showing you before, essentially people skate on liquid water. Okay, so liquid crystals are other examples of that, and I recommend you read the book about that. Okay, we are done for the lecture today. Basically, if you have any questions, you can ask me in my office, but I've covered what I need to for liquids and solids. So next week I'll continue with solutions and talk about solutions, but this kind of addresses enough you can understand next week's lab combined with the energy chapter, as well as the liquids and solid stuff, colligative properties and other things related to these. Okay, any other questions, please email me or whatever. So we're done for the day. Thank you very much.